Thank you. Thank you. So, hi, I'm Ivan. I work at Google Project Zero. We do security research. We try to make zero-day attacks hard. Now, I don't want to be talking too much about myself today, but if you want to know more about what I do, or if perhaps you'd like to start doing security research, but you don't know how, feel free to talk to me after the talk. So now let's talk about web browser security. And before I get started, I have a bit of a confession to make, and that is that the techniques presented in this talk are not going to be anything new. They are in fact quite old and quite well known. But in my defense, that is kind of the point of this talk, to take an old and well-known bug hunting technique, which is the DOM fuzzing, and see if we can still find good bugs with it in the modern browsers. So while the techniques themselves are going to be old, the issues you're going to see in this presentation are going to be real issues affecting real browsers that are being used today. So let's talk about web browser security. And why would we talk about web browser security at all? Specifically, why would we talk about web browser 0 days? Well, one possible reason why is because if you make yourself or your organization a target interesting enough for advanced attackers, well, then there is a good chance you're going to get owned by a browser vulnerability. Of course, that's not science fiction. We've seen that happen in the wild. So I have a couple of examples here. So for example, we've seen a mobile Safari vulnerability being used against a human rights activist. We've seen Firefox bug being used against Tor browser users. We've seen several Internet Explorer vulnerabilities being used in targeted attacks. And these are just from the last year or so. And these are just the ones that we actually know about. So in fact, what we might be looking at here is just the tip of the iceberg. So right, now let's look at the specific part of web browsers, which is DOM. So what is DOM? Well, DOM is W3C standard, which defines a set of objects that the browsers need to implement. So if you take a look at the slide here, you're going to see some of the objects in the image. If you know anything about HTML, then these objects shouldn't be anything new to you. So these are like your standard HTML elements, but the DOM doesn't really define only those types of objects. There are various other types of DOM objects, such as attribute nodes, style sheets, event objects, etc. And besides just defining the objects themselves, the DOM also defines how these objects may be scripted. So at the bottom of the slide here, you have a simple example where we are essentially generating a new element and then assigning a property to it. Right. So each browser basically needs to have a component that implements all of these DOM objects together with their properties and methods. And this component of the browser is called a DOM engine. And historically, DOM engines have been a great source of browser vulnerabilities. And that is, of course, not to say that they have been the only source of web browser vulnerabilities. In fact, there have been many others, such as plugins, scripting engines, etc. So keep that in mind throughout this presentation, that you won't really get the whole picture of a browser security. You're going to get only information about a part of it. So in fact, you might not see the whole elephant. You might see a significant part of the elephant, perhaps the trunk, but not the whole elephant. Right, so how do these DOM vulnerabilities actually look like? And here I have a small example, which is a code that triggers the bug that was used against Tor browser users. And we won't be going into the details of the vulnerability here, but what I want to draw your attention to is the general structure of the sample that triggers the bug. So as you can see here, we have a snippet of HTML code. In this case, it has an embedded SVG image in it. There is also some JavaScript code in the on-click handler. And so this is typically the general structure of these samples that trigger DOM vulnerabilities. You have some HTML code, you have some JavaScript code, and in some cases you also have some CSS code. And none of this is actually malformed. It's actually, for the most part, correct, but it is put together in such a way that you wouldn't commonly see on a web page. So when we are talking about DOM fuzzing, we're essentially talking about creating samples such as this, that create random snippets of HTML, JavaScript, and CSS code that are syntactically correct, for the most part also semantically correct, but are not something that you would commonly see in a web page. So how do we do that? Well, my general approach to fuzzing is to essentially always create my own fuzzer, and that might seem counterintuitive at first, but whenever I create my own fuzzer, I'm going to do something different than what is already out there, and it might be a very small thing. But that very small thing might have a butterfly effect, which might cause my fuzzer to generate certain samples with greater probability and enable my fuzzer to discover bugs that other fuzzers might have overlooked. Or it might happen that I just like writing fuzzers, so pick the actual reason. So for this project, for this piece of research, I created a new fuzzer which we call Domato, and it is generation-based, which means that it always generates a new sample from scratch, and it is also grammar-based, which means that it generates the sample based on a set of grammars. So here you have a small example, a simplified example of a CSS grammar that, well, generates CSS code. And so if you're familiar with CSS, this should be fairly readable. So CSS is basically, CSS code basically consists of a set of rules. And each rule contains a selector part followed by a declaration part enclosed in curly brackets. And then the selector part can refer to various HTML elements such as anchor element or an audio element. And the declaration part consists of a list of properties, and these properties can be, for example, background property or border property, and each of them have their values. So I think the grammar syntax here should be rather straightforward to read. So you have a set of symbols which are enclosed in angle brackets, and you tell the fuzzer how each of these symbols may be expanded, and one symbol can of course include other symbols in its rules, and then those symbols are basically expanded recursively. So I showed you a CSS example. Can we use the same technique to generate HTML? Well, yes. Only minor quirk here is that I'm using angle brackets as kind of characters that have a special meaning in the context of my grammar syntax, and HTML does as well. So we need to escape them. So in this case, you'll notice that I'm using LT and GT symbols, and these are built into the fuzzer, and they evaluate to greater than and less than and greater than character, respectively. And these are just some of the built-in symbols. There are others as well. And interestingly enough, we can use pretty much the same basic principle to generate programming language code as well. So how do we do that? Well, we essentially tell the fuzzer, hey, now I'm going to write programming language lines, and I'm going to to write them between the begin lines and end lines statement. And then anything in between can be potentially output by the fuzzer as a programming language line. The fuzzer is going to select one line and at random, more or less, and fill it out. One other addition here is you can see that some of the symbols have a new attribute in them, and that essentially instructs the fuzzer, hey, instead of generating a symbol of the specified type, instead just create a variable of the specified type here. And then that variable can be included in subsequent programming language lines, and one variable can be included in multiple language lines afterwards, which contributes to generating more interesting samples. So as you've seen, grammars are kind of big part of my fuzzer. So how do we actually create those grammars? Well, in the past, I've experimented with various approaches, such as manually just writing them or automatically extracting them. But for this particular project, I used a hybrid approach, where I started with a set of grammars that were automatically extracted. So for example, from Chrome IDL files, which contains information about JavaScript interfaces, and from Chrome layout tests, from which I extracted HTML properties, CSS properties, and SVG properties as well. So I started with this automatically extracted set of grammars, but then I did manual pass over them to try to improve them as much as I can. And one example where this kind of makes sense is given here. So for example, an automatically extracted grammar might tell you that HTML input element has a type property which takes a string, but not any random string makes sense in the context of this property. There are in fact a limited number of strings which make sense in this context. So that's one example where an automatically extracted grammar might need improvement. And we're not quite done here. There are a number of other features that DOM Fuzzer needs to support in this day and age to be able to find interesting samples. But I won't be going into each one of these in detail. Instead, I'm going to share the good news with you today, and that is that this fuzzer is in the process of being open sourced. It should be open sourced really soon. I'm aiming for next week, but I can't make any promises. But in any case, it's going to be open sourced fairly soon, and then you would be able to play with it and modify it as you see fit. So how do the samples generated by my fuzzer actually look like visually? Well, in most cases, they don't look like much, I have to admit. But in some cases, they produce samples that are quite visually appealing once rendered in the browser. So, well, I guess if my career in information security ever fails, I might try to frame one of these and sell it off as modern art. And also, if you ask me how some of these samples were generated by the fuzzer, I would have absolutely no idea, and I think that's the beauty of fuzzing. Right, so now that we have a fuzzer, let's test it, right? And we decided to test it against 5 of the most commonly used web browsers out there, and each of the browsers have their own DOM engine, which you see in the brackets. And we tried to give each of these browsers an equal treatment. So we decided to give each of the browser 100 million iterations of the fuzzer. And 100 million iterations might sound like a lot. And in some sense it is. For example, if you just want to fuzz on a single machine, and if you assume that a single iteration is going to take you 10 seconds, and keep in mind that the samples generated by my fuzzer can be quite large, then you would come to a fuzzing time of around 32 years. So of course you wouldn't do it that way. But if you have a fuzzing cluster of say 300 machines, then the same number of iterations would take about a month or a bit over a month, and that's more realistic. So how much 300 machines for a month would cost you? Well, I did some calculations on Google Compute Engine, and it turns out that if you use the weakest available virtual machines, then you would be able to do that for about $1,000. And that might be a lot for a hobbyist, but if we are assuming advanced adversaries whose budget measures in millions or possibly billions of dollars, or if you're selling exploits for hundreds of thousands of dollars, then $1,000 doesn't seem like such a large investment at all. So how did we actually test those browsers? Google Chrome was probably the easiest because Chrome security team has their own fuzzing cluster, which is called Cluster Fuzz. And essentially, all I needed to do was upload my fuzzer to Cluster Fuzz, and then it magically works. Story done, happy end. Firefox and Safari we fuzzed on internal Google infrastructure, which is Linux-based. And you might be wondering at this point, well, how did I fuzz Safari on Linux, because Safari doesn't run on Linux? Well, essentially what I did instead of fuzzing Safari was to fuzz WebKit GTK Plus. And WebKit GTK Plus uses the same DOM engine as Apple Safari. And then I verified each of the crashes I reported against the Safari build that was actually running on Mac. IE we fuzzed on Google Compute Engine on a cluster of Windows Server 2012 machines. And Microsoft Edge was kind of the most difficult because we couldn't run it on Google infrastructure, at least not easily, because Edge only runs on Windows 10. Windows 10 still doesn't run on at this point on Google Compute Engine, and unfortunately Windows Server doesn't support Edge. So what I did instead was to fuzz Edge on Microsoft's own cloud, which was kind of interesting when people from Microsoft Cloud Support called me and asked me, "Hey, what are you using our cluster for?" Right. So in addition to that, we made some build or configuration changes to those fuzzers to be able to catch bugs more easily. And in the case of browsers where we could make our own builds, that basically meant building with sanitizer. So Firefox and WebKit were built using ACE and sanitizer, and Chrome on Cluster Fuzz already runs built with various sanitizers. For IE and Edge, obviously, we didn't have our own builds, but what we did was to enable page heap for the relevant processes, which kind of serves the same purpose. And we also made sure that the garbage collector in each of these browsers gets called periodically, which is important to catch use after free issues, which are quite common in web browsers. So finally, here are the results expressed as the number of bugs. And I'm going to spend some time on this slide. But before I dive into the results, I want to say two things. Firstly, all the bugs you see here are security bugs. So in case the fuzzers found some other type of issues, like issues that would affect only the browser stability, but wouldn't necessarily have a security impact, these aren't counted here. And also only the bugs that affected the real released stable version of the browser's mentioned are counted here. So for example, if we fuzzed against a development build of the browser, we made sure that the bugs were actually working against a released version of the browser before counting them here. Right, so now let's look at the results. And my general impression is that most browsers actually did quite well, because if I use the same methodology 3 or 4 years ago, my impression is that I would be getting probably an order of magnitude more issues. So I think that shows a clear progress for the most part. Now, and also the differences between the browsers are quite small. So you really can't say that one browser did worse than the other because one browser had 2 more bugs, because that difference is just not statistically significant. So please don't make such claims based on my talk. On the other hand, there is a browser that kind of clearly stands out from the rest in terms of number of bugs, and that is Apple Safari, that is its WebKit DOM engine, and that is kind of interesting for several reasons. One of those reasons is that we know that advanced attackers are very, very much interested in the Apple's platform. And the other reason is that up until a couple of years ago, Chrome and Safari used the same DOM engine, which was WebKit. And then at some point, there was a split, and Chrome team created their own fork, which they call Blink. And now there are quite significant differences that indicate that either in the meantime, the number of bugs in Blink got significantly reduced, or that there was a number of new bugs that were introduced in WebKit, or some combination of the two. But I really don't want this presentation to be seen as Apple bashing. So instead, I asked myself, well, what can I do to improve the situation? And one thing I did was to contact Apple as soon as the results started popping in, and I told them, hey, I'm fuzzing browsers, WebKit is not doing so great. I'm interested in sharing my tools. I'm interested in sharing my methodology. Long story short, now they have a copy of my Fuzzer, so I really hope they use it to make the situation better. And as I said again, I think most browsers did quite well, and there are various reasons for that. So, for example, this is kind of interesting. Internet Explorer and Edge use this mitigation for use after free vulnerabilities, which is called memgc. And there is actually a registry flag with which you can disable this mitigation. And then when you disable this mitigation, what you see is a bunch of other issues popping up. But of course, this mitigation is not disabled in the real configuration, and there are no, for the most part, there are no obvious bypasses. So this is kind of the example of a mitigation that really works and is really useful. So now when that is over with, let's look at the fun part, and the fun part are the actual bugs. So here I have an example, and it's interesting for It's interesting for a number of reasons. One reason why it's interesting is because it is a vulnerability that affects 2 browsers, which are Chrome and WebKit. And this means that this is a pretty old vulnerability that must have been introduced prior to the Chrome and prior to the Blink and WebKit split. And the other reason why it's interesting is that there are basically two separate issues here. But before I go into the details, I first have to go over some background. So in the DOM, there is something which is called a shadow DOM. And the shadow DOM essentially enables you to implement one HTML element using a set of existing HTML elements. And there is a special type of shadow DOM, which is called the user agent shadow DOM. Now, the property of the user agent shadow DOM is that the JavaScript code running on the web page should never be able to modify it. Now, what you have here is you can see in the sample code that I have a keygen element. And if you don't know what a keygen element is, it doesn't matter. I included a small image on this slide. And as you can see, it kind of looks like another HTML element, which is the select element. And in fact, that is exactly how it is implemented in WebKit and Blink. So you have a keygen element, which has a user agent shadow DOM, which contains a select element. And what happens in the JavaScript code here in this page is that basically caret range from point function in this particular situation gets you an object that you can use to modify the user agent shadow DOM, which, as I said before, you never should be able to do. And then what happens after that is that the fuzzer basically prepends a text node into this shadow DOM. And what happens after that is that the web browser assumes that the first element inside the shadow DOM is going to be a select element. So it's just going to take it and blindly cast it into a select element, but it is no longer a select element because we changed it. It is now a text node element. So we are casting a text node element into a select element, so this is a type confusion vulnerability. And so what I mentioned before is that there are kind of two separate issues here. The first one is getting into the user agent shadow DOM. The second one is the type confusion. And the type confusion part, you can actually really easily see in the source code because it's just blindly casting whatever element to a select element. However, you really can't reach this type confusion vulnerability unless you're also able to modify the shadow DOM. And why caret range from point in this particular instance returns you a shadow DOM is very, very not easy to see by looking at the source code. And in fact, there are a number of other elements that are implemented using shadow DOM. Well, it turns out that this only ever worked in the combination with the keygen element. So I think this is a pretty good case for why fuzzing is important, because you can find these vulnerabilities that are sometimes quite difficult to see from the source code. And you can also catch vulnerabilities that only ever manifest when a certain set of conditions are true. And I have a bunch of other bugs here. Unfortunately, I'm running out of time, so I'm going to have to skip over them. But these are all public. You can find all of these in the Project Zero bug tracker. So if you're interested in learning more, feel free to look at them. Feel free to analyze them, see what issues they triggered. So right, let's jump to the conclusion now. And so, despite the DOM fuzzing being really old and quite well-known technique, it can still find interesting bugs. That's kind of the bad part. The good part is that while it does find bugs, it finds less bugs than it used to, and also and that in itself forces bug hunters to look to do more manual review, and that is a good thing because manual review has a higher barrier to entry if we're talking about advanced attackers. So, so what can you do? If you are a browser vendor and you're not fuzzing your browser code, you're going to have a bad time. How not to have such a bad time? Well, do fuzzing at scale. Do fuzzing using multiple fuzzers. Because, for example, I really don't believe that WebKit folks don't fuzz WebKit. I think they do, but either they are not doing it at the large enough scale, or the fuzzers they are using have blind spots. And realistically, all fuzzers do. And that, of course, it extends to mine. So if you find some blind spots in my fuzzer, please let me know. If you are a browser user, or if you're in a position to select a browser for your organization, please try to make an informed decision, which I realize is very, very difficult because there is just not that much objective information out there. And I think this is an area where security community can do a better job by sharing that kind of information. And of course, if you are a security researcher, you can help by reporting bugs to the vendors. And as I said, my fuzzer is getting open source, so feel free to play with it, feel free to modify it. And if you find if you find something that enables you to find more bugs, please report them to the browser vendors. With that, I kind of ran out of time. I'm going to defer to the organizers whether we have time for questions or not. But in any case, thank you very much for listening. Okay, seems like we have time for questions. On what? Tor browser. My insights on Tor browser. Wow. So this is kind of a complex question, and I think there are kind of two issues you should be very careful with the Tor browser. One issue is that it is based on Firefox, and Firefox at this time doesn't have a good sandbox. So in fact, you pretty much at this point need only one vulnerability to own Firefox, whereas for the other browsers you need to. I know that Firefox folks did do some work on the sandbox, but I'm not sure at which stage it is. And I also know that the Tor browser folks kind of created a sandbox of their own, but it was kind of easily breakable at that point, so it's kind of young. Give it more time and perhaps it improves. Now the second issue I have with the Tor browser is, well, how difficult it is to find a bypass which will not be a browser vulnerability, but which will be something that would basically allow the browser to bypass Tor and connect to a resource directly. So that's kind of my worries with regards to Tor browser. And if you're running a Tor browser, my advice would be to run it inside a virtual machine, which both adds another layer on top of the browser, assuming of course your virtual machine is up to date, and also that the virtual machine, if you configure the virtual machine so that it can't access anything other than the Tor, then it kind of might add to your protection against these Tor bypasses that I mentioned.
One update of the virtual machine. It is, you can say I'm wrong, but it's also easy to run tails in the virtual machine to have a OS that is already hardened for stuff.
So I'm not an expert on tails. I don't know how vulnerable it is, so I wouldn't make any claims whether to support it or not support it.
You should not run tails unless your hardware is not compromised. For example, light heater, if you compromise with that, tails won't help you.
Yes, of course.
How did you trash crashes and security bugs? Because I assume you had tens of thousands of crashes. How did you make distinction between the regular safe crash and security bug?
That is a great question. So how did I triage crashes, and how did I determine which are security bugs and which are not? Well, in the cases where I had the sanitizer builds, it's quite easy because the sanitizer actually is actually able to recognize what type of issue it is. So, for example, you have use after free issues which potentially have security impact. You have heap out of buffer out of bound issues which potentially have security impact. So it's pretty easy to recognize this just from the sanitizer report. In the case of browsers where that weren't run with sanitizers, well, in those cases, well, what you end up getting in practice when you fuzz browsers are essentially a large number of null pointer dereferences, and these are kind of easy to spot and automatically triage as well, and then anything that isn't a null pointer dereference, but that is only going to be a relatively small number of issues, you can essentially triage manually to determine the security impact. Sorry? Well, I use ASIN because I think it's a de facto standard for these things. Of course.
Including yours.
Yep.
And that several browsers have similar vulnerabilities. So is there perhaps a database of, I would say, let's say, use cases, test cases, that if you're a browser vendor, you could use instead of using multiple fuzzers in order to regressionally test your new versions of the browser?
Right. So that's a great question as well. So if we can. So considering that we have bugs that affect multiple browsers, can we use tests to find bugs in one browser using tests from the other ones? And well, yes, that happens, and I'm not sure if the browser vendors do it though. If not, they probably should. But I am aware of a couple of security researchers who did exactly that and were able to find interesting issues that way by taking essentially tests from one browser and then running it against another browser. Well, okay. So the first question is how to get into the browser fuzzing, and well, you can. I guess a good way to start is that question would kind of take a long time, but I guess how you can start is looking at what other people are doing And as I mentioned, the browser fuzzing is not a new technique, and other people are doing it as well. So you would be able to find other presentations on DOM fuzzing as well. So take a look what other people are doing. Take a look at their fuzzers if they're available. And by just looking at what they do and looking at vulnerabilities, you might have some ideas of your own. So try to implement them and try to see how well it works. What was the second question, sorry? Genetic algorithms. So I didn't really experiment with genetic algorithms. What I did experiment with, and what I think is kind of might happen in the future, I experimented with coverage-guided DOM fuzzing. So basically, kind of AFLE principle, but with mutations that are specific to DOM. Unfortunately, in my experiments, I didn't really find bugs that I wouldn't find using your ordinary DOM fuzzing, but it is perhaps possible to do it in a better way that I have been doing it. And I think whoever finds a way to include coverage information into in a meaningful way in DOM fuzzing might be the next king of DOM vulnerabilities. Are we out of time? Okay, we are probably way out of time, but thank you.